Newton's laws provided the scientific world with a remarkable ability to study forces and motions in nature, as well as an unswerving confidence that various other laws could be deduced by observing the natural world. But Newton was not able to solve the riddle of heat and its companion phenomenon, light, which baffled researchers until well into the 19th century. This lecture is going to explore the nature of energy, which is defined as the ability to do work. My two principal objectives in this lecture are to first define the subtle concepts of work and energy, and then to catalog the many different kinds, these surprising and interchangeable kinds of energy. These forms of energy include kinetic energy, which is the energy of motion, potential energy, which is stored energy, energy waiting to be used. We have wave energy, including waves in solids and liquids and in gases. There's heat energy, the energy of atomic motions. And then the more subtle forms of energy, light energy, which travels at 186,000 miles per second. And finally, the energy associated with mass. What attributes of nature enable a system to change? What allows you to exert a force? These are deep and profound questions, and their answer lies in the study of energy, a scientific field that's called thermodynamics. Now that word thermodynamics comes from two roots, thermo for heat and dynamics for motion. So thermodynamics is quite literally the study of heat in motion, how heat moves. Unlike Newton's laws of motion, the laws of thermodynamics did not spring forth fully formed from one mind. There was no eureka moment, as it were. Rather, these ideas emerged gradually from many, many different researchers. And it was primarily in the early and the mid-19th century that the laws of thermodynamics were finally formulated and understood in a systematic way. It was actually only much later that they were set down in a form that we use today, in a form that you and I could understand in just everyday language. And that's what I'm going to try to do in the next few lectures. The difficulty in understanding energy is epitomized by a simple candle. Light a candle, look at the flame, and ponder two questions, age-old questions. What is heat? What is light? Are heat and light a kind of force? Can they cause an acceleration? Well, heat is certainly associated with some kinds of motion, but hot objects don't always accelerate. Are heat and light in themselves a kind of motion? If so, what forces cause the acceleration of heat and light? Do heat and light have mass? Do they have some kind of substance, physical substance? Even though heat and light are amongst the most tangible objects and phenomena in our material world, their origins are amongst the most subtle and difficult to deduce. Ultimately, an understanding of both heat and light depends on the essential but very abstract concept called energy. The definition of energy requires introduction of another concept, and that concept is work. It has a very specific meaning in physics. Work is one of those everyday words that we run into all the time in science, which actually has a very specific scientific meaning and a more colloquially meaning in our everyday life. We've seen several of these terms. Motion is one, force, acceleration, energy. Those are all terms that we use in everyday life, but they have very specific scientific meanings. Well, work is expended whenever a force acts over a distance. And the formal definition of work is a force times a distance, a force acting over a distance. The unit of work is a joule. And that's when 1 Newton is exerted over the distance of 1 meter. A Newton meter, if you will. In the English system, the appropriate unit for work is the foot-pound, but I want to refer to newtons and joules. So if you have a lime, which weighs, remember, the force it exerts is about 1 Newton, and you raise it 1 meter, you've done a joule of work. Or alternatively, if you like to think in terms of fig newtons, 7 fig newtons make 1 Newton, and once again 1 meter, we've done a joule of work. Work is only done if the force is exerted in the same direction as the object's motion. So the Earth does no work on the moon because the moon's movement is always at right angles to the gravitational force. So if you have a swinging ball, the kind of swinging over your head, once it gets going, once it starts that circular motion, and I stop, it'll keep going forever unless there are frictional forces and other forces that slow it down. I'm not doing any work at all now because the ball is moving at right angles to the direction of the force. You do work if you push your car along the road. If your car runs out of gas, as long as you're pushing it and it's moving, you're doing work. But if the car doesn't move, no matter how hard you push, no matter how much sweat you work up, you're not doing any work. By the same token, if you lift a heavy weight, you're doing work. But if you just hold it out, no matter how tired your arm gets, since you're not exerting a force over a distance, you're not doing any work. That's the formal definition of work. Now we come to the definition of energy. Energy is defined as the ability to do work. That is, energy is defined as the ability to exert a force over a distance. So any physical system, any phenomenon that allows you to exert a force over a distance is a kind of energy. Energy is a measurable attribute of physical systems, but unlike mass or motion, it has a mysterious, intangible quantity. You can't really hold energy per se in your hand, but you can hold objects that have the potential to exert a force over a distance, so those objects have the attribute of energy. They contain energy in some sort of way. It's little wonder that this concept of energy was so poorly defined until the middle of the 19th century, that it took scientists so long to come to terms with it. Energy was difficult to recognize and describe in part because it can adopt so many different forms in our surroundings. There are many, many different ways to exert a force over a distance. Let's think about the kinds of motions that we see around us and analyze what form of energy then is involved in those motions. There are three really common kinds of energy in our everyday life. They're real obvious, and these are the ones that scientists first recognized. These are called kinetic energy, potential energy, and wave energy. These have long been recognized for their ability to exert a force over a distance. Perhaps the most intuitively obvious form of energy is that carried by objects in motion, kinetic energy. If you flick a crumb off your sleeve or throw a ball, the ball goes through a window, it can break things, it can exert a force over a distance, it can do work. And therefore, the ball in motion, your finger in motion, anytime you move something, you're causing kinetic energy, which has the ability to do work. The kinetic energy of any object can be calculated from its mass and its velocity. And it turns out, in this case, force equals 1/2 of the mass times the velocity squared. This formula is easily derived from Newton's second law, which says force equals mass times acceleration. And you need a couple other definitions, classic definitions as well. You need to have the standard formula for acceleration, velocity, and distance that relates to these three parameters. For example, distance equals 1/2 acceleration times time squared, and also velocity equals acceleration times time. And with those three standard definitions, you can derive this idea of kinetic energy. Here's how you do it. Kinetic energy has to be force times distance. Well, the force is just simply mass times acceleration. And distance, d, is the distance traveled. But distance from our previous equation is equal to 1/2 at squared. So that means the kinetic energy, you just substitute now, kinetic energy equals 1/2 m at squared. Now there's one other trick. Remember, the velocity is equal to a times t. So here we substitute at for velocity for at, and we get kinetic energy equals 1/2 mv squared. And that's the equation for kinetic energy. This equation allows us to calculate the relative energy of a car traveling at different speeds, for example. And you may be surprised at the result. think, for example, about the kinetic energy of your car when you travel 35 miles per hour compared to 55 miles per hour compared to 75 miles per hour. In the equation for kinetic energy, the 1/2 m part cancels for all these three. So all you have to worry about here is just the relative amount of energy is proportional to v squared. So let's look at this. 35 times 35 is 1,225. If you go up to 55 miles per hour, 55 times 55 is 3,025, more than twice the kinetic energy. And you go up to 75 miles per hour, 75 times 75, it's 5,625. That's more than 5 times the kinetic energy than when you're traveling at 35 miles per hour. So you may just approximately double your speed, but you have many times more kinetic energy. Because kinetic energy is proportional to velocity squared, that means as you increase in slight increments your velocity, you can greatly increase your energy, and that has consequences. There are two in particular. One, as you go faster and faster, you're going to consume more gasoline because you have to put the energy into the car to get that kinetic energy. So your gas consumption, your miles per gallon, is going to start dropping off dramatically as you go to very high speeds. The second thing is the danger if you get into an accident. Because when you get into an accident, all your kinetic energy gets converted into other kinds of energy, the smashing of your car. At higher velocities, there's much more energy that has to be converted into that damage of the car. And therefore, high-speed crashes are proportionally much more damaging than low-speed crashes. It's not just a simple linear proportion to velocity, it's velocity squared. Okay, let's look at a different kind of energy. Many natural systems store energy, and the energy is waiting to be used, just waiting to exert a force over a distance. These varied forms are called potential energy. The most obvious form of potential energy in everyday experience is due to gravity. The stored energy of water behind a dam, for example, or the weight of a pendulum, of a weight in a grandfather's clock that drives the grandfather's clock. That's stored energy, gravitational potential energy. And it's energy that's there by virtue of a mass's position within the Earth's gravitational field. If it's up high, it's waiting to drop and release energy, converting gravitational potential energy, for example, into kinetic energy. To raise a mass m to a height h takes work, and work is force times the distance, so you can calculate gravitational potential energy just by our simple definition. Energy equals work, which is force times distance. But the force of gravity on an object is just mass times g, so that's mass times little g, gravitational acceleration, times height. So you can use this equation, mgh, as the energy contained by an object, to make all sorts of calculations. For example, a 2-kilogram mass, if you want to lift that 1 meter, how much energy does it take? Well, you just substitute into the equation 2 kilograms times 9.8 meters per second squared, that's the acceleration due to gravity, times 1 meter is 19.6 joules. So that's the energy required to raise a 2-kilogram mass 1 meter. There are many other kinds of potential energy that are very common in our day-to-day life. We have chemical energy stored in food, chemical potential energy, or in matches that you use to light a candle. We have chemical potential energy also in batteries. There are chemicals here ready to release energy. In refrigerator magnets, there's certainly energy there, and it can exert a force over a distance by picking up objects. You also have potential energy in a stretched rubber band. You can take a rubber band and pull it back, and there certainly is potential energy here, and then you can let it go and off it flies. So there's all kinds of potential energy that we use in our everyday life. Third kind of energy, wave energy. Waves represent a very efficient kind of kinetic energy in which energy can be moved long distances without actually having to move lots of mass from one place to another. There are two kinds of waves that accomplish this feat in different ways, slightly different ways. You have transverse waves. And these are sort of like the waves in a sporting event at a stadium where people stand up and then they sit down, stand up and sit down. the people are moving up and down, the wave appears to move around the stadium. And so the direction of the wave is at right angles to the direction of the movement of the individual people or the particles involved. That's very much like the waves on the surface of the ocean, when you see ocean waves moving along. You also have compressional waves. Compressional waves would occur if you could imagine a whole bunch of people being crowded together and one person sort of stumbles and leans into, and that wave gets pushed through from person to person to person. So that's where the direction of the wave is the same as the direction of the motion of the individual pieces of the object. You can exhibit some of these properties of waves just with a telephone cord. And if you have one of these long cords and you're sort of in a boring phone conversation, you can start playing with it because you can learn some of the characteristics of waves. For example, waves have velocity. Now the cord itself is not moving from one place to another, but you can see the motion of the wave going from one end to another. You can imagine if I had a domino or something balanced on the end of this telephone wire and did that, it would flick off. I could exert a force over a distance, even though I'm not moving mass from here to there. I'm not doing anything other than just flipping and sending a wave going through. Waves can travel through water, as in the ocean. They can travel through sound. That's through the atmosphere. They can also travel through solid materials. Earthquakes are waves that can transfer tremendous amounts of energy through the solid earth. So there are lots of different kinds of waves, and we'll meet several of those throughout this course. Kinetic energy and potential energy, wave energy, these are all pretty obvious ways of exerting a force over a distance. But once scientists understood the definition of energy, they began to see some other subtle kinds of energy. And I want to tell you about these three other kinds of energy that finally were identified. These are heat, light, and mass. The nature of heat was a matter of intense debate for centuries. On the one hand, there were supporters of the caloric theory. This was often associated with the influential French chemist Antoine Laurent Lavoisier, who lived from 1743 to 1794. Let me tell you about Lavoisier, a fascinating character in the history of science. He was born in 1743, the son of a prosperous French lawyer. He lived in Paris. He received an excellent education. He rose to a position of power and prestige in pre-revolutionary France. He turned from his expected career in law to science, and he became enthralled with chemistry and with mineralogy, and he used part of his family fortune to construct and equip wonderful research laboratories in France, in Paris, France, and in a nearby suburb villa that he had. Lavoisier was a champion of liberal social reform, and he worked within the existing political system to try to effect those reforms. During the French Revolution, however, he was targeted as a sympathizer of the former regime, and he was executed by guillotine on May 8, 1794. The following day, the great French mathematician Joseph Louis Lagrange said of Lavoisier, quote, "It took only an instant to cut off that head, and 100 years may not produce another like it." Lavoisier's scientific work was wide-ranging, but he was best remembered for all sorts of meticulous chemical studies, which involved careful documentation of both the products and the reactants of various chemical processes. This was unusual in his time to look at the products and the reactants both and weigh them out and carefully analyze all of them. He was especially interested in the chemistry of burning. He played a major role in the discovery of oxygen, as well as the role of oxygen in combustion and in oxidation reactions such as rusting. In this work, Lavoisier espoused this caloric theory, which described heat as a massless fluid, a fluid that could flow from one object to another. And if you think about the way candles behave or fires behave, this isn't such an odd idea. Candles and other combustibles appear to consume their store of caloric and just evaporate away. If you heat certain objects, they seem to expand, sort of like a waterlogged log expands when it soaks up water. Perhaps objects expanded when they soaked up this caloric, this fluid. But other scholars disagreed. They saw heat as a manifestation of motion at the atomic scale, and thus they thought of heat as a mechanical property of matter. This debate was ultimately resolved by a very unlikely figure, the opportunistic American-born inventor Benjamin Thompson, who lived from 1752 to 1814, who called himself and granted himself the title of Count Rumford. Well, Rumford led a remarkable, adventuresome life. At the age of 19, he married an extremely wealthy widow, 14 years his senior. One person was said to be the wealthiest widow in all of Massachusetts at the time. And he settled in Rumford, Massachusetts, and gave himself this title of Count Rumford. He became a Tory spy. That was during the American Revolution, but he had to flee to England. He abandoned his wife and his infant daughter in 1775. That's when his position in the colonies became untenable, and he was about to be arrested for his work as a spy. Later in his turbulent life, he was forced to flee England, once again on suspicion of spying, this time for the French. He also had the distinction of marrying Lavoisier's widow. You remember Lavoisier? Well, he married that widow who was also very wealthy. That marriage failed miserably with much recrimination on both sides. Turbulent life for Count Rumford. Well, Rumford was always fascinated by the phenomenon of heat. And he conducted numerous experiments to try to improve the use of heat in everyday life. Indeed, his invention of the modern-style cook stove and the modern fireplace gained him fame and, for a time, a great degree of wealth for his own inventions. At one point in his life, he was appointed commandant of police in Bavaria, of all places, and one of his duties there was to supervise the boring, the construction of cannon. The way you make cannon is you poured a mold of brass, and then you actually had to drill out the bore of the cannon. This was a cacophonous process, and it resulted in lots of heat and lots of, you can imagine the process of taking a huge drill and actually turning the barrel of the cannon and keeping the drill bit fixed. You had solid bronze barrels, and as you drilled through, you generate lots of heat. What Rumford noted was, I suppose, the unremarkable fact that when you had a dull drill bit, you produced a lot more heat than if you had a sharp drill bit. But if you think about the caloric theory, if you had a sharp drill bit, you're actually cutting out more of the bronze, and so you'd think you might produce more heat with a sharp drill bit. But no, in fact, if you had an extremely dull drill bit and you didn't drill anything at all, you just kept grinding and grinding and grinding, you produced the maximum amount of heat. And so Rumford realized that the heat was produced by friction, which is mechanical action. And so he proceeded to study this phenomenon. He said, quote, "I was led into these investigations by accident and in some measure against my will." I'm not sure what he meant by that. In any case, in 1797, he designed a clever experiment in which he carefully insulated the barrel of a cannon and purposely drilled it with a very dull drill bit in a tank of water. And here's what he reported. This is a quote from one of his scientific publications. "At 2 hours and 30 minutes, the water actually boiled. It would be difficult to describe the surprise and astonishment expressed on the countenances of the bystanders on seeing so large a quantity of cold water heated and actually made to boil without any fire." This experiment clearly showed that heat was a consequence of mechanical work. I think you can convince yourself of this if you just rub your hands together. If you do this for a while, your hands start getting very, very hot, and you really can't keep it up for too long because of the heat generated just by friction. The caloric theory was buried forever when English chemist Humphrey Davy did a very similar kind of experiment. He was a brilliant public lecturer. He succeeded in melting ice on a cold winter day in London just by rubbing two pieces of ice together outside. I think it's worth taking a minute to tell you about Humphrey Davy. He was one of the greatest lecturers in science of all time, a real person to be revered for someone in my profession. He was born in 1778 in Penzance on the coast of Cornwall. He was born in a middle-class family, but he had a solid education. He was drawn apparently to poetry and literature, though he also loved nature and mineral collecting. And mineral collecting was a great thing to do in Cornwall because of all the old mines, the tin mines and so forth in that part of the world. So he must have developed quite a mineral collection. The untimely death of his father in 1794 forced Humphrey to take up the apothecary trade, which led to more formal exposure to chemistry. He read assiduously. He set up his own modest laboratory to perform chemical research. And he gained quite widespread attention after the publication in 1800 of his book, Researches, Chemical and Philosophical. Now, based on this study, Benjamin Thompson, that is Count Rumford, invited Davy to become a lecturer on chemistry at the Royal Institution of Great Britain. And it was there that Davy established his reputation as one of the most popular lecturers in the history of science. We're going to learn more about Davy's work in chemistry in Lecture 20. But in any case, what Davy did was develop a flair for kinds of public demonstrations. So when there was this cold, icy day in London, he used the occasion to show that you could melt ice simply by friction. He turned it to his advantage. He was always thinking about the world in that way. Yet another convincing demonstration that heat is a form of energy is provided by heating water in a closed cylinder with a piston. Now think about this experiment. You have a cylinder that's closed, you have water in that cylinder, and you have a heavy weight sitting on top of it. If you start heating up the water and it boils and it expands, just the expansion of the water and the formation of steam is going to raise the weight against the force of gravity. You're exerting a force over a distance. So just by applying heat at the bottom end of the system, you do work. So that's another demonstration that heat has to be a form of energy. By the way, we now know that heat is actually a form of kinetic energy at the atomic level. Heat represents the motion of individual atoms. And we'll learn a lot more about atoms a few lectures from now. But just the idea that this is really a form of kinetic energy at the microscopic or submicroscopic scale. It's fascinating. There are other forms of energy besides kinetic energy, potential energy, wave energy, and heat. We also have radiation. Light that travels 186,000 miles per second. That's about 300,000 kilometers per second. Think about the sun, the energy that you get from the sun. You go out on a sunny day and you can feel the warmth of the sun as it comes down. That energy is traveling through the vacuum of space. So it has to be a form of energy different from the ones we've talked about so far. Indeed, the sun is the principal source of energy at the Earth's surface. And it's a form of light energy. When you see light, when you turn on a flashlight, for example, the light's coming to you at 186,000 miles per second. It's a form of energy that travels through all sorts of medium, including a vacuum itself. And finally, we have one of the defining discoveries of the modern age of science, Albert Einstein's recognition in 1905 that mass itself is a form of energy. This is according to the very familiar equation E equals mc squared, where c is the speed of light, 300,000 kilometers per second. This means that the quantity of energy in everyday objects is unimaginable. You can do a calculation, for example, a half kilogram, a 1 pound loaf of bread, for example. How much energy is associated with the mass? Just plug into the equation E equals mc squared. You have the mass, half a kilogram, which isn't very large, but the speed of light, 3 times 10 to the 8th meters per second. And then you have to square that quantity, which gives the huge number of 4.5 times 10 to the 16th joules. 10 to the 16th joules in just one loaf of bread. While most of this energy is forever locked up in the mass around us, scientists have discovered special circumstances where they can convert mass to energy. And we're going to talk about that a lot more in the chapters on nuclear energy in Lecture 22, for example. Let's summarize these ideas about energy. Energy is it's a subtle concept. Its characteristics are neither intuitive nor obvious. To define energy, you first have to define work, which is a force acting over a distance. Energy, then, is defined as the ability to do work, the ability to exert a force over a distance. And once you've defined energy, you can start cataloging the different kinds of energy about us. There are 3 obvious kinds of energy. Kinetic energy, that's the energy of motion. Potential energy, which is stored energy in various forms, gravitational or elastic or chemical. That's energy just waiting to be used. We have wave energy that transfers through various medium, solids, liquids, or gases. And then there are less obvious forms of energy, things like heat and light, and ultimately mass as a form of energy. Now that we've defined energy and cataloged these various kinds, the stage is set to present the 2 great laws related to energy, the laws of thermodynamics.